So, all is ready to start? Yep. Окей. Можешь потом закрыть дверь? Okay. Do you have any questions about last topic, about graphs and Brett's first search?
Can I ask about algorithms or homework?
Solve homework.
Yeah.
No. As I know, you have 1 week to do first homework. After that, we can solve it on the lecture. And now, okay. Other questions? Okay. And today we will talk about depth first search, shortly DFS, and it's similar algorithm as Brett's first search, but it has other idea in center of it. So we'll start with, of course, definitions. And today we will talk about trees and forests. As I think you know, a tree is connected graph without cycles, and the forest is a union of trees. Okay? It's simple. Yeah? Nice. So, about depth of first search, about idea of it, if we remember BFS, yeah, it like waves on the water. Remember it? And DFS has as idea, it like a thunderbolt that start in one vertex and go down to the deepest side of the graph. Okay. So about algorithm. Firstly, we will start in one point and follow the edges while we can get new unexplored vertex that adjacent to the last. Okay, and when we end first step, yeah, for example, in this vertex, we can say that there are no any adjacent vertices that are unexplored. Okay. So when we say this, we go to the second step of this algorithm and back to the last point that have any adjacent unexplored vertices and recursively explore them. Okay. And if we end first 3 steps and we have any unexplored vertices in the graph, so we say that, for example, if it is undirected graph, we say that this graph have some connected components and then repeat this algorithm for other component. Okay. So it's about implementation. Go to the example. Yeah. And there are coverings and 2 important numbers that we have to each vertices in the end of the algorithm. Okay. And each algorithm have time that we explore it, and time when we finish to explore adjacent vertices of this vertex. So, for example, about pseudocode of the algorithm, we can see that at the start of the our algorithm, our graph had all vertices like white vertices that have no any times, as we see on this graph. Okay. Then we start with one vertex and say that it has time or explore time equal to 1. Yep. Then we visit this point. Okay. Then we set time to this point and see do we have any adjacent vertices to U vertex that haven't been explored. Okay, and if we have these adjacent vertices, so we visit them too. Okay, and then repeat this cycle while we have any adjacent unexplored vertices. And if we have explored all adjacent vertices, we say, okay, we finish this vertex and say that it's time then we finish explore this vertex. Okay. So about example, we start with the point A. Then we see that there are one adjacent vertex B that is unexplored. Yeah, and go to this vertex. Okay, and say that time 2. It's time when we explore vertex B. Okay. Any questions? No? It's simple, very. Okay. Then we repeat algorithm for B, repeat for E, for C. Then we see that F has no any adjacent vertices, so we finish to explore it and go back to the vertex E. Yeah, and we see that vertex E have different adjacent vertex that have now been explored. So we go to the vertex D, we visit it, and see that vertex D has only one adjacent vertex A, and it has been explored. Okay. Yep.
They have one question. They want you, if it's possible, to share the PDF.
Share PDF. Okay. Yeah. I send it now. Okay, I sent it to the chat.
All right.
So yeah, we finish with vertex D. We say that each vertex has only one adjacent vertex, and it has explored. So we finish with D, we finish with E, we finish with B, and we finish with A. Yeah, and we see there are no any other unexplored vertices, so we have only one connected component. Okay? Any questions? Hmm? Last sentence. Okay. We see that there are no other unexplored vertices. So we say that graph has only one connected component. Okay. But if you see, for example, this graph is directed. So when we say that it has only one connected component, we see that, for example, from F to B, we has no path through the edges, yeah, because of the direction. But, for example, if we start with vertex F defense, we see that only one vertex can be reachable from this vertex. Yeah, and then when we repeat algorithm for vertices A, for example, B, E, D, we see that, for example, from B we can reach F and we connect this graph. Okay. So of course we are lucky that when we start with vertex A, we can reach all vertices in the graph. But if we start with F, for example, yeah, we can transform our algorithm and see, of course, all these connected components. Okay. Yeah.
A connected component is a component in which you can reach any other points from them.
Yep. Now I say about small connected component. It defines as you can erase directions of the edges and then see which vertices can be reachable from each other.
So the definition, for example, the definition we have for connected components when the graph is directed.
Okay, we have two different definitions, and for the second definition we will talk because of other algorithm that we will talk in 10 minutes,
Okay.
I think. Okay. So now you can see, for example, for this graph, that if we erase directions, yep, it will be a connected connected component, and it's one of the definition of connectedness of the directed graph. And about strongly connected component we will say in some minutes. Okay. And for example, in this graph we have three strongly connected components, 1, 2, and 3. But of course we will talk about it not now. So, yep. About time and space complexity, as we can say, as for breadth first search, yeah. Remember that breadth first search has time complexity equal to O from number of vertices and number of edges. Remember it? Nice. And so for DFS we have the similar results. Do you understand why it is true? Why it is true? Why we have this time complexity and this space complexity?
For the first one, because we will go to every node and we will also explore
Yeah, yep. Yeah.
edges.
Yeah, because as you can see, when we go, for example, to node D, we of course search all of incident edges to this point. Yep. And then we go to the any vertices. So we have v number here, and we need to visit all edges from the start point of this edge, and so we have this number here too. Okay. And about time complexity.
We will store it as a vector.
Yeah. Because of times.
Yeah, because we know how to check, write which nodes we already visited.
Yeah, of course. But if you can see here, we have big node class, yep, with color, with parents, with final time, and so with discover time. So we can do big class node and have no other arrays in the algorithm, because we store it in this node. Okay. But of course, there are any other implementations of DFS, and you can use other, not this. Okay. So about trees and edges, yeah, we can see here we have DFS tree. Yep. It has black edges, and we have edges in the graph that are not in the tree DFS. Okay, so there is classification of edges. Yep.
Why do we use 4 nodes? Is it the same as 0 and 1?
Why we use colors? Okay, we need to understand which vertices we have already explored. So if you use, for example, a bool variable to this, it's equal to this coloring. So if we have no stored this information, as you can see, we can cycle our algorithm. Yep, because we go to the D vertex and then say, oh, okay, it has adjacent vertex A, and we go to A, and then we have infinite cycle in our algorithm. Okay, so oh, I can see chat now. Nice. So to stop our algorithm and not to visit vertices that we have explored, we need to store this information in the node. Okay.
You can see it.
Now, can you move it to the right? Yeah, nice. Yeah, I see it now. Oh no. Yep, nice.
Full screen?
Yep.
Full.
Oh, okay. Why do we and could you explain what is time in the pseudocode? What is the time in the pseudocode? You can think that time is equal to time in the real, but we store it as a variable because we need to understand in which order we visit each vertices. Because we have different applications of this algorithm, and so we need these times, and we say in some minutes why it is good to store time when we explore vertex and time when we finish to explore it. Okay. And do you have any questions? Nope. All is understandable. Nice. And about classification of edges, we can see this picture. There are black edges that includes to DFS tree, and there are 3 types other edges. For example, red edges name as back edges that have a start point in the vertex A and end point in the vertex that is ancestor of vertex A. Okay, and formal definition here. Yep, that H U to V names as back edge if V is ancestor to vertex U. Okay. So if there are other direction of this edge, for example, we see that if it is vertex U and this is vertex V, we say that U is an ancestor to the vertex V. Yep. So we say that it is forward edge. And so we have cross edges that connect that connects vertices that has no order in this tree. Okay. So it's about forward edges. We say that edge that starts in vertex U and ends in vertex V, that is, it is forward edge if U is an ancestor to vertex V. As we see in the tree, U have the path to the vertex V.
Okay.
Yep. So, about applications of DFS. Yep, there are different applications in the real tasks, for example, solving mazes, and for example, job scheduling. And of course, it has different applications in exercises that appear in graph algorithms, and we see next on the next slides that DFS is useful in this direction. Okay. So about first task and solution with the DFS. For example, if we have directed graph and we want to find a cycle in this directed graph, and of course we say that path names as cycle if every edge has directed from vertex E to vertex E plus 1. Yep. If, for example, we reverse this edge, it will not be cycle. Okay. So there are we want to find directed cycles. Okay. How DFS is used in job scheduling? Could you please explain shortly? Okay. Okay. I will write some example here. about job scheduling. For example, if you have different tasks in your job, yep, and one task depends on other task. For example, to start the lecture, I need to create a presentation, for example. And so we write it like an directed edge from 1 to 2 vertex. Okay? And so we write dependencies of the tasks. Yep. For example, and of course, we try to avoid these cases because of we cannot solve cycle tasks without do it in the same time. Yep. So we think that this graph has no directed cycles. And then we can order these tasks like this, for example. 2, 4, 6, 5. In this order, because if we do task A and task 3, we can do task 2. Yep. And we can, for example, do this task in this order. This is about job scheduling. Is it understandable? And for you too?
Yeah.
Nice. And I'll go to the slides. It's about cycle detection and about ideas that we see in the job scheduling. We can see if we have directed cycle graph that is shortly named names as DAG. Yep, as DFS, as BFS. We'll use a short abbreviation of this sentence. And then we will see this graph has no directed cycles. Yep. And we want to represent this graph as tasks on the other board when we use it to schedule our job tasks. And our solution of this task names as the topological sort.
Well, DAG.
Hmm?
DAG, directed cycle graph.
Directed acyclic graph. Yep. Of course, we have cycles that have edges in the both directions, but we have no cycles like this. Yep. That have edges in the same direction. Understandable? Yep. So, for example, we can use DFS and induce from this numeration of our graph. And for example, if you say to me different numbers from 1 to 15, say some, or say some edges that we have in the graph.
B
B, from B to N, for example, yep. And we see that B have 8 number and N has 13 number, yep. And if you see on this figure, you can see that any edge that starts in vertex V and ends in vertex U, it has number of vertex V smaller than number of vertex U. For example, there is edge F to R, and F has 4 number, and R has 5 number. Yep. And for any edges in this graph, there is condition that is completed in this numeration. Okay. And about pseudocode of topological sorts, it likes DFS. It very it's very similar to DFS, but we can see that we have list L that stores numeration of vertices that we explored. So when we finish with vertex U, for example, we push it to the list L. Yep. So numeration of the graph that we have and order that we set our vertices equal to post order of reverse order of finish times of the vertices. You can see. For example, here we have directed graph. Yep. And we start DFS from one vertex. For example, from E. And we go to the B, go to the D, finish with it, explore E, and other steps of DFS. Yep. And then we see, for example, when we end with D, it is first vertex that we finished with it. Yep. We push it into the list, and it has the smallest order in our numeration. So then we go to the B, go to the adjacent vertex that have no explored, and finish with it, and push it to the list. Yep. So then we finish with vertex V, vertex B, and push it to the list. Then we go to the F, go to the G, and finish with G. No. We go to the C vertex and finish with it. And then go to the G, finish with it, then finish with F vertex, and then finish with R vertex. So it is this numeration is equal to the order that we get from the finish time of each vertices. Okay? Understandable?
Yeah.
Right.
I think 3 we don't have.
Hmm?
3. Number 3.
Number 3 in this example. The last.
Number 3.
Yeah.
How would we get it?
In this list. How we get it is in this list.
We got from 5, and then we.
Okay. So let's to understand where we start this DFS algorithm. For example, we will start from 3. Yep.
We start from 0, not include 1.
But let's me to talk about if we start with 3 and so then I tell you points where we reach one vertex. If we start with 3, I use different no articles. Yep. Yes. Nope.
Don't hand inside.
Here. Oh, yes. Nice. For example, if we start with 3, we go to the 2 vertex. Then we go to this vertex and go to this vertex. Then we finish with 5. It's time to add it in the list. Then we finish with 6 and we add to the list. Then we finish, we go to the 4 and then finish with it and push it to the list. Then we finish with 2. Yep. And we finish with 3. Okay.
From 3 to 2. 2 is not connected with 3. How to make it?
So 2 is not connected to 3, but 3 is the parents of the 2. And when we finish with 2, we say that 3 has no other adjacent unexplored vertices. Then, if we see in the algorithm, if there exist unexplored vertices, repeat the algorithm for them. Yep. And we see in the pseudocode that function dfs repeat for each vertex our algorithm. And we tree that we have on the left board equal to result of the dfs visit function. And then function dfs try to understand each vertex has black color or no, and it finds that one has white color and starts dfs visit from this vertex too. And then our algorithm says that it new vertex that we start our dfs, and then we have no adjacent unexplored vertices, so we end it and push it to the list. Understandable? Mm-hmm. Nice. Sorry, still I don't understand the logic for time in dfs. Masoud, do you understand about discover time and finish time? About when we start to explore vertex, we say that it is time when we discover and set discover time to the time that we have. Then, when we finish to explore all adjacent vertices to the vertex U, we say that it's time when we finish with vertex U and set that is time that finish time is equal to time that we have. And I can make other example of DFS, for example. Masoud, can you tell, do you need any other example? Oh. So, it's bad. I think, okay, I'll explain, repeat to explain. Okay, so time is equal to, for example, real time. So we say that U point D is equal to time when we discover our vertex U, and U point F is equal to time when we finish to exploring adjacent vertices. So in the end of DFS, each vertex has two times when we start to explore it and when we finish to explore this vertex and adjacent to it. Oh, see, nice. So, about topological sort, it was example. Okay, and we have other time too. Okay, about other tasks that can be solvable with DFS. It's about a strongly connected component. It is other definition of connectedness in the directed graph. Okay, and as you can see on this figure, there are four parts of our graph that contains vertices that are reachable from each other. Yeah, as you can see, for example, if it is A vertex, if it is B vertex, then we have path from A to B, directed path, of course, and we have directed graph, directed path from B to A. And for example, if we get vertices from different strongly connected components, for example, if it is A vertex and it is B vertex, then there are two cases. For example, as you can see, there is path from A to B, yep, that and there is no path from B to A. But of course, if you say, for example, that it is vertex A and it is vertex B, there are no any paths in both directions. No path from A to B and no path from B to A. Yep. So we can say that it is strongly connected component, and this is other strongly connected component if two conditions are completed. Yep, condition that two vertices in connected component have two paths from 1 to B and from B to A. Yep, and that I said about vertices from the different components. Okay, it's about the definition of strongly connected component. So about finding this connected component. As we can see on the previous slide, if we draw each connected component as one vertex, so we see directed acyclic graph. And so if we start, for example, in one vertex in a green connected component and go down to the other vertices as in the depth first search. Yep, we go to the point that has no other adjacent vertices that are unexplored, and in this time we say that it is this vertex has connected components that has no edges from these components to other components. I repeat it. First vertex that we finish with it contains in connected component that has no edges like this, that starts in this connected component and ends in other strongly connected components. So, for example,
Like, if there was such case, it would be a strongly connected component.
Yep. Yeah. Of course, if we have, for example, edge from this component to this, we have one strong component, but not the three. Okay, and other viewing of this figure that, for example, if we end in vertex in this connected component, and if we reverse all edges in this graph, then there is no edges that starts in this component and go to the other strongly connected component. It's simple too. If we reverse all edges, of course. So, about algorithm that solves this task. Okay. First step is simple. It's only DFS. But then, in the second step, we reverse all directions, and then we start DFS from the last point, from the last vertex that we visit in the DFS. And all vertices that we can reach in new graph with reversible edges, these vertices will be in the strong connected component of vertex that we visit last. And then we repeat this algorithm to each for each vertices that we don't visit in the DFS visit. So, for example, if we have our graph that we saw a few moments earlier, so we can start DFS from I forget. Yep, we start with this vertex. If we start DFS from this vertex, then we go to this vertex, then we finish with it, 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 and numbers on this vertices are equal to finish time of our DFS. Okay, I can draw discover time, but it isn't important to work of this algorithm. We need to store only finish time of vertices. Okay? So then when we have graph with nodes that store finish time of DFS, then we reverse all edges and repeat DFS visit function, DFS visit, from vertex that has the biggest number. Okay? Then we start with vertex 32. Yep. And as you can see in the last figure, there are only 5 vertices that we can reach from this vertex in new graph, and all of these vertices will be contained in strongly connected component of vertex 32. Okay. Then when we end DFS visit, we see that we visit these vertices, and we have 30 like the biggest number in other component of graph that we don't visit earlier. So we repeat our algorithm to this vertex, but of course we cannot explore vertices that we explored before it. For example, we see that this orange vertex was explored before this, and it contains in this strongly connected component. So we see that and these two. So we say that this yellow vertex has no adjacent vertices in a reversible graph. So it makes small, strongly connected component. Okay, and when we say it, we repeat our DFS visit for the next biggest number, for example, 29. Yeah, and we see that there are paths from 29 to 24 or to 28, 27 and 26. So it is other strongly connected component. When we finish with red, yellow and orange connected components, we see that in the other parts of the graph we have 14 as the biggest number. And so we start DFS visit from this vertex, and we visit 2 vertices. Then when we end it, we see that in the last part of the graph we have 12 the biggest number, and we make last step of DFS visit and so see that in the last strongly connected component of our graph. Okay, and so I think I can make other example about. Oh yeah.
We start for example, if we start from 32, then that.
Oh, please repeat. Mr. Yeah.
Yes. We went to 31.
Yep.
And then after that, 30, 29,
So it's
30, and 29. We explored this part. And then we went back to 30.
no. In the firstly, I write times equal to finish times of each vertex. And diff is that we start in 32 has no path like this. It starts with 32, 31, then 14, 13, 12, 11, 8, and 8 it is first vertex that we finish with it. I repeat it with the example, okay? And other example, for example, okay. For example, we have this graph initially. And we will start with, for example, this vertex. We open it. Then we see that this is unexplored vertex adjacent to it. Then we see this, and this, this, and this. And we see this vertex has only one adjacent, but it is explored. Yep, so we finish with it. We go to this, finish with this, finish with this, etc. Okay, then we store only finish time, and I erase time when we discover these vertices. Okay, and these numbers equal to numbers that I draw in the figure on the slides. Okay.
Why the last one is number 8? Last one? Yeah,
This 8 number. Why? Because when we start with this vertex, it was first time, second, third, fourth, fifth, sixth, seventh, and we finish with it in the one time plus in the 8 time. Understandable? Or?
Yeah, if we apply example, then how do you get it?
How
You get it?
11. Okay, when we finish with it, vertex, it was 8 number. Then I back go back to
Yeah,
the
now
visuals and go to this and open and finish it. Finish with number 10. And then I finish with this vertex with number 11. Okay. I try to put it in vertices. Then, what is the second step of the algorithm?
We reverse the
Reverse all edges. Yeah. So I need to erase direction and set other direction for this. So I use other color to get quicker this. And erase. No, to avoid any conflicts with understanding of this graph. Okay. Is the graph with reverse edges. Yep. Then we see, okay, we have 16 as the biggest number of these vertices. And then we start from these points our first strongly connected component in the graph. And we go to the 14, go to the 15, and say, oh, there are no any adjacent vertices, and our first strongly connected component. Or for example, we can go back and see that there is no any adjacent as DFS. Yep. Then we see we can forget this part of the graph and see there is 13 is the biggest number of part that we haven't get in the first step. So we start second defense visit from this vertex and see, okay, we have only one adjacent vertex, but it has already explored in the first step. Yep. So it is new strongly connected component. Then we see that 12 is the biggest number. And we start DFS visit from this. We go to 10, 11, go to 8, and that's all. Yep. It's the last strongly connected component. Understandable? Guys. Okay. Okay, and let's get free time, 10 minutes, for example, and then start with the last part, all networks and algorithm with it. Okay? Yep.